Okay, I just want to go through one of these problems where we have to determine an absolute max and an absolute min on a given closed interval for a particular function, and the process by which we got to do that. Remembering that our traditional way to go about to find relative maxes and mins is to take the derivative and set it equal to 0, find all the places where the derivative is either 0 or undefined, those are the critical numbers, and then that's it. Those are going to be places, and then maybe put them on a sign chart, and you can tell whether it's going to be a max or a min. The problem with that, though, is in a situation like that, what you're doing is finding these local high points or local low points, and maybe if it's undefined, you might see something like that. So the calculus is going to find a place like that, or that, or that, where the function goes from increasing to decreasing or decreasing to increasing. What we're going to get in these kind of problems, though, is like a little bit of an added twist is, since it's on a closed interval, maybe our graph goes like this and stops right here. Well, if we're trying to find the lowest y value of this whole function, this point right here is not going to qualify. Even though he's a local min, this point is clearly lower. Likewise, we could have a curve that kind of goes like this and finishes up here. And although nothing's happening special at these things, calculus-wise, like their slopes aren't any number in particular, slopes aren't 0, the slopes aren't undefined, but those places represent absolute maxes and absolute mins. So we need to go about the process of finding out where these guys are and testing their y values against these guys. And then when we find the biggest one, we get the absolute max. When we find the smallest one, we get the absolute min. So the process starts off the same in that we're going to take the derivative. So the derivative of sine squared, we bring the 2 down in front and drop the power to 1, but then we've got to think chain rule and come back and take the derivative of what's inside, which is cosine of x. So we're taking the derivative of sine, which is cosine. And then the derivative of cosine is actually negative sine. Now, cosine and sine are functions that are defined everywhere, so we're not going to have any places where the derivative is undefined, but we can set this equal to 0. And in order to do that, probably the easiest way to do it is recognize that we can factor out a common factor of sine. So we get sine of x coming out, and we'll have 2 cosine of x minus 1 equals 0. So either the sine of x equals 0, or 2 cosine of x minus 1 equals 0, which is going to mean the cosine of x is going to be a half. Now, on the interval from negative pi to pi, we have to think about our circle here for a second. Negative pi would be coming over here, and pi is going that way. So as far as the sine being 0, the sine is going to be 0 anytime when you're on the x-axis. So here at 0, it'll be 0 at pi, and it would also be 0 at negative pi. So we're going to get 3 solutions to this. X equals negative pi, 0, and pi. And it's kind of worth mentioning that 2 of those critical numbers are endpoints. So a big part of these problems is making sure that after you get the critical numbers, what we're going to wind up doing is checking the y value at all these critical numbers, but you also want to make sure you check the y values at the endpoints. Now these are kind of doing double duty. Not only are they critical numbers, but they're also the endpoints. Anyway, back to our circle here to figure out when the cosine's a half. Cosine is kind of going with your x value, so we need the cosine to be a half is going to be over here on the right side, and that would be the triangle that would kind of look like this, where this is 1 and this is 2 and this is root 3, and that angle there is pi over 3. So it's going to happen at pi over 3 and again down at negative pi over 3. So there's 2 solutions to that at negative pi over 3 and pi over 3. So now that we have the critical numbers on the interval and the endpoints of our interval, all we have to do is test the original function, because we're trying to find the maximum value of the original function. All we have to do is test these values, all 5 of them, in that function and see which one gives us the biggest y value and which one gives us the smallest y value. So I'm just going to proceed kind of in order. We're going to check negative pi, which would be the sine squared of negative pi plus the cosine of negative pi. And the sine of negative pi, again over here, is 0. So that's just going to be 0. And the cosine of negative pi, remember the coordinates over here, negative 1 comma 0. Cosine's negative 1. So that gives us a y value of negative 1. So we just kind of store that in memory. Maybe I'll put a little blue box around him so we can come back to him later. Now we need the y value at negative pi over 3. I'm going to kind of go in ascending order here. So we need the sine squared of negative pi over 3 plus the cosine of negative pi over 3. Well, luckily I have my picture here. At negative pi over 3, our triangle looks like this. The sine is negative root 3 over 2, but we're going to square that. So we're going to wind up squaring negative root 3 over 2 and adding that to the cosine of negative pi over 3, which is 1/2. Now, once you square that, that's going to become 3/4 plus 1/2, which I'll write as 2/4, which is 5/4. So there's our second y value. Moving along, we're going to test our third one. We're going to go to 0 now. We already did him, we did him. So we're going to go to 0, and we're going to get the sine squared of 0 plus the cosine of 0. Sine of 0 is just 0, and the cosine of 0 is 1. So we get 0 plus 1, we get a 1 there. So far, this guy's winning for at max, and this guy's winning for min. So let's check what's happening at pi over 3. And I think you're going to see that sine squared of pi over 3 plus the cosine of pi over 3 is going to be exactly the same as when it was negative pi over 3. This is going to be root 3 over 2 squared plus 1/2, which is going to turn out to be 5/4 again. So we'll put a little box around him, and he's now tied with this guy. And so we just need to check one more. We've got to check the function evaluated at pi. And f of pi is the sine squared of pi plus the cosine of pi, which is 0 plus 1, which is 1. So as it turns out, looks like we have, we've got, oh wait, the cosine of pi is not 1, it's negative 1, because he's over on the left side. So that's going to be negative 1. So we have two guys, this one and this one. So we have absolute mins at x equals negative pi and pi, and the absolute maxes occur at x equals the 5/4 guy, which was negative pi over 3 and pi over 3. But again, the big thing about this is that once you get these critical numbers, you test the y value in the original function, and you have to test the y values at the endpoints in the original function, just to see who's biggest and who's smallest, so that you can catch a situation where you might have an endpoint y value that's bigger than or smaller than one of the relative mins or maxes that we found. Anyway, that's the way those go. That's pretty typical. It'd be like a test level question, pretty straightforward. And there you go.